we can start. Just a sec. Let me check if anyone is planning to join. Okay. Yes, I think we can start. Okay. So in the last class, we have discussed about, some of the aspects of the course, and also we just started with the basics of robotics. Okay. So we have discussed about these stuff, and then we jumped into the robotics concepts, right? So we have discussed what is a robot, okay, and then we are planning to discuss these topics, okay. This session will be mostly covering using slides, and there are some web resources as well. So I can share that web resources. It's actually mentioned in the links as well, so you can have a read on. Those are like it's not simple pages. It's actually like big content, I will say. There are a lot of things to read. So maybe this week you can invest some time on reading these references. Okay. Yeah, I can mention whenever whenever we start discussing these topics. Okay. So today we will be starting with what is a robot. That we already seen last class. Then we will jump into robotics in a nutshell, then different kinds of robots, okay, then different applications, then kinematics and dynamics, then we will see how to build a robot, basically. Okay, what are the various steps that we have to follow to build a robot, then what are the steps or what are the basically the steps to choose sensors, actuators, and computing unit, the compute unit for your robot. Okay, then we will see what are the frameworks for programming the robots. Okay, so this is the agenda for today's session, and I'm planning to discuss it for 1 hour. Okay, so after 1 hour we will stop. Okay, or maybe I will take maybe 10 more minutes extra if it is not finished. Then after that we can conclude. Okay, so let's start. So yesterday we have seen what is a robot, and most of you may inspire from watching these movies and all, and even I am also inspired from like doing some stuff in robotics by watching these movies like Terminator, Iron Man. Okay, this is actually an inspiration, and also the Big Hero 6 that I mentioned yesterday. So, but in reality, it's much different than than we are seeing in the movies. I have shown the book, right, the handbook of robotics, and you can just check that book. I can say it's a Bible of robotics. Okay, so then you can analyze what is the reality. Okay, so this will happen in all technologies. For example, if you heard about deep learning, if you watch some videos, it's actually very interesting, like detecting objects, then predicting something. Okay, the videos actually looks good, but if you start implementing deep learning stuff, okay, it's not easy at all. Okay, and if you are trying to learn deep learning to the core, then it's actually the foundation is core mathematics actually. Okay, I will say it is much difficult than robotics in the max level. Okay, if you compare. So if you take any technologies from the surface layer, maybe it may looks good and it may looks interesting, but in reality, when you approach or when you try to learn, then only you will understand the difficulty. Okay, so I will ask you to be in the reality, not in the imaginary world of robotics. So it's actually not very easy that you think. Okay, it will take a lot of time to understand concepts, and you have to dedicate a lot of time to understand all these things. Okay, it's not an easy one. So we have seen what is a robot. So basically it's a machine, intelligent machine. Okay, and it is having sensors, okay, to sense the environment around it, and then it is having a computer, So the sensors is attached to the computer, then the computer is taking a decision, and the decision is going to the actuators, and that is performing some actions. Okay, so this is what a robot is. Okay, if you take any robot, you can find these blocks. Okay, this is actually the loop. This loop continuously running, like reading from the sensors, processing the data from the sensors, then producing some control signals and going back to, sending back to the actuators. Okay, so this is a detailed diagram of robot. It's not much detail, but what I tried to show you is that in a robot there will be multiple actuators, multiple sensors, and even multiple computers. Okay, so if you take a complex robot, for example, the Boston Dynamics robot, you can find maybe 3 or 4 computers. Okay, that is connected in a same network and doing the computation together. Okay, and also you can find microcontrollers along with the full-fledged PC. Okay, so these all belongs to the computing. Okay, so these are the main components in the robot. Okay, and this is an example for a robot that is an obstacle avoidance robot. It's very simple example. So I just want to show you that how this sense, think, act loops works. Okay, so for an obstacle avoidance robot, basically the sensor, it will have some sensors to detect the obstacle. Okay, maybe an ultrasonic distance sensor or sharp IR sensor or anything that can detect, or maybe a LiDAR. Okay, and then the sensor will give the detected output to the computer. Then the computer is taking the decision. Okay, so the computer it will compare whether the object is too close or too far. Okay, if it is too close, then the computer will ask to the motors like just to stop or just move away. Okay, and this loop will keep on executing. Okay, so this is an example for an obstacle avoidance robot, and you can see the sense, think, act loop. Okay, yes. So yeah, a very basic example, obstacle avoidance robot. This is the implementation of the same. So it is having an ultrasonic sensor, distance sensor, that is this sensor. Okay, and then the sensor is connected to some microcontroller. Okay, then if there is an obstacle, it will go away from the obstacle, or it will just roam around. Okay, yes. So then we have seen the main blocks of robot. So now what is robotics? Okay, again, this is my understanding of robotics. I got it from various web resources, and then I just created my own definition. Okay, so robotics, according to me, is an interdisciplinary branch of engineering, okay, which deals with the conception, design, simulation, and manufacturing of the robotic system. Okay, so from the description, you can understand, like, it's an interdisciplinary branch of engineering. Okay, it involves many branches of engineering, and it deals with the conception, design, simulation, and manufacturing of the robotic system. Okay, so when you get a requirement, you have to conceptualize it, then you have to design it, you have to simulate it, then you have to manufacture it, the actual hardware, then you have to deploy it. Okay, so robotics, it's a combination of different domains, engineering domains, and it deals with the complete design, from the requirements to the manufacturing of the robotic system. Okay, it involves all the aspects of a robot. Okay, from the concept to the manufacturing. So that is robotics. And again, a brief history of it. I'm just quickly go through it. I'm not sure how many of you heard these things. Like, it's actually, when you open any books in robotics, you can find these things. Okay, so actually robot means forced labor. Okay, forced labor. You are actually like, if you check the industrial robots working in car manufacturing units and all, we are actually giving the commands to do some job, right? The robot is doing lot of job automatically with human commands. Okay, and we are not paying any wages to robot. It will just consume the electricity, that's it. Okay, so it's like a forced labor. That's what the robot means. It's a Czech word. Okay, and it's initially I think it's mentioned in a play called RUR 1920, I think, by a person called Karel Capek. I'm not sure the yeah, I think this is the first time they're using the word called robot, that came from robota. Okay, so that's actually the robot now. Okay, robot, the word. And then you may heard about the three laws of robotics from Isaac Asimov. Again, simple things like there are three laws of robotics, mainly like it's actually mentioned in most of the robot movies, basically. Like a robot will not injure human being, then a robot must obey the orders, and it should protect its own existence, and it should not conflict with the first and second. Okay, so simple things. Yes, and this is another important stuff. So when you talk about robotics, it involves various domains actually. Okay, so you can find the robotics involve AI. Okay, and then we can find computer vision. So if you integrate computer vision to robotics, we can say it's a robotic vision. Okay, it's another branch. Then robot control, biorobotics, aerial robotics, autonomous cars, kinematics, robot learning, medical robotics, swarm robotics, speech processing. I mean, if you check the Bible, if you check the handbook of robotics, you can find all these domains. Okay, and you will get a lot of reference from that. Okay, so if you are interested in robotics, okay, in general, and if you want to focus in some domains, for example, I am interested in mobile robotics, wheel robotics, and nowadays I'm also like planning to work on the legged robot, because I am like seeing a lot of future for legged robotics, because you may have seen the Boston Dynamics legged robot, right? Sport Mini. So the advantage of legged robotics is that legged robots is that it can travel or it can move to any kind of plane. Okay, imagine if it is a wheel robot, it is very limited. It can only travel in a plane, but that is not the case for legged robotics. So I'm also planning to focus in that area, but like I'm mainly interested in these autonomous navigation, SLAM, mapping, then localization, all those stuff for wheeled robots, then legged robots. So these all are my interest. So if you want to specifically focus into one area, for example, if you're going for a research, you should focus into some domain. Okay, because robotics is a very big branch, and you have to focus into some domains. It may be like self-driving cars, or it may be like a legged robot, anything. Okay, according to your interest. Okay, yes. And who is a robotics engineer? So that is the next definition. Again, my own definition. So it's like I'm seeing a robotics engineer is like a full stack engineer. Okay, full stack. I think you may heard about the full stack, the word full stack. Meaning like he should have good understanding of mechanical engineering, electronics, and computer engineering. I mean, most of the engineering branch that is coming in robotics. Okay, maybe he's not an expert in all of things, all of these branches, but at least he should have an understanding. Okay, for example, me, like I started from electronics background. Okay, from my early childhood, I started working with some circuits. Then after creating some circuits, I got interested in computers, I think in 7th standard or something. But at that time, I didn't even work with computers. but we had some chapters about computers, so I was so fascinated at that time. From that, electronics, then computer science was my passion actually. Then when I started creating prototype mechanical engineering. I mean, not an expert, but like I have some idea about it. So what I'm saying is, like, when you work with robots, okay, either you can focus in some domains, okay, like you can fully focus into motion planning or control, or maybe perception or navigation, that is there. But again, it will be better if you have an overall understanding of all the system. Okay, for example, embedded programming, then controls, then perception. I mean, and you can focus in one domain. Okay, like me, I'm focusing on these slam, then localization, all those stuff, focusing on that. But I can do other stuff like embedded or perception, or all the things as well. Okay, that's what I meant, like full stack. Okay, so if you are working in a startup, then you have to work like a full stack engineer or developer. Okay, so it will be better to understand all the aspect of robotics, and you can focus on specific areas. Okay, yes, so that is a robotics engineer according to me. And now I just want to show you different kinds of robot, okay, and application. So for that, I'm using a web resource, that is my blog. So this is the link. Okay, I will mention this on the notes, by the way, and I can share the slide as well. So in this blog, I have documented most of the popular robots. Okay, so you can find. I'm just scrolling. Okay, you can read this blog. Okay, for more understanding. So as of now, I'm just going through the list. Okay, industrial robots, then collaborative robots. Collaborative robots are like a sub of industrial robots, and then you can find warehouse. Then you can find the pages here, so you can just navigate to different pages. Then consumer robots, then drones. Okay, then what, medical robots. Okay, so I also put some videos for better understanding. Okay, and for the entertainment industry, you can find a lot of robots in entertainment. And in medical robotics, you can see this image, right? So it's called the Da Vinci robot, which is for doing like different operations, medical operations, surgery. Okay, a Da Vinci robot. Then education robots. Then yeah, actually there are a lot of categories of robotics. I mean robots. Then research robots, mainly dedicated for doing research. Then military and security robots for inspection and military purposes. Then self-driving cars. This is actually one of the hottest area in robotics now. And if you are planning to do a master's abroad, okay, you might be end up in a self-driving car company, because there are a lot of opportunities in this domain. Okay, in the self-driving car company. So yeah, so if you are working in a self-driving car company, then you have to focus maybe on mapping, then navigation, localization, or perception, or anything. But at the same time, it will be better to have an overall understanding. Okay, then telepresence robot. So I think you can go through this list. Okay, so I think you will get a good understanding of different kinds of robots. Okay, and I'm not saying all the types are mentioned in this blog. Okay, but I think I try to incorporate most of the types of robots. Okay, okay. Then generally, like when you work with robotics, you will categorize like the robots into robotic arm and mobile robots. Like when you started a course in robotics, you might like have a differentiation. Like the courses, mainly the courses are mostly talking about robotics arms. Okay, if you take any robotics book, okay, then you can find the robotics arm equations and all, and then they will talk about mobile robots. Okay, yeah. Okay, so now we are going to discuss some concepts in robotics. Okay, just a second, let me start the video, I mean the webcam. So just a sec. Yeah, so yes, so when we talk about robotics, if you take a book in robotics, then the first chapters or first two chapters will be explaining or discussing about these two topics called kinematics and dynamics. Okay, kinematics and dynamics. So this is a very important topic that is discussing in most of the book. Okay, so I just want to say some things about these two terminologies. Okay, so if you take our body, okay, so we have two hands, right? We have two hands, and using our hands we can take the objects. Like I can take a water bottle from here. I can put the water bottle anywhere in this 3D space. It's easy, right? It's very easy. Even I don't need to think much about positioning this water bottle in any position or any pose. Okay, I can do that. And also, if I want to move from my current position to another position, okay, I can just walk. Okay, I can just walk and reach. Okay, so if a robot is planning to do these two tasks, okay, if a robot is planning to do these two tasks, then how can it perform? I mean, the robot has to pick this object and position this object like this, and the robot has to move from one position to another. Okay, so for robot is a machine, right? So it doesn't have any intelligence. The intelligence is in the software, right? So in order to in order to uh, in order to make an application using a robot, okay, for picking an object and placing it somewhere like this, we have to solve some problems. We have to solve some problem, and that problem is actually there for human also. That problem is there, but our brain is handling that. Okay, the problem is we are actually using our hand, right? We are actually using our hand to take it. Okay, take the object. Okay, so first the problem is the hand should move towards the object, right? Towards the object. Okay, then the hand should take the object or grip the object, grasp the object, right? Then hand should move to some coordinate. Okay, so in order to move our hand, we have to adjust the joints, right? We have to adjust the joint. Are we doing any computation for moving this joint? Like we have to move this joint 90 degree, then we have to move the joint 30 degree? No, right? It's all doing by our brain, right? But in case of robot or robotic arm, okay, like our arm, a robotic arm consists of joints. Okay, instead of these natural joints, it will have motorized joints. Okay, each joints will have a motor, right? And the motor has to be controlled, obviously. So for robot there is no brain. Okay, and the brain is a computer. Okay, and the intelligence is in the software. Okay, so it's the robotics engineer responsibility is that the robotics engineer could able to compute the joint values if you are working with a robotic arm, it should compute the joint values. If we give a hand position, for example, I'm giving a hand position to here, so it should compute the joint values, okay, automatically. Then it should grasp, then again compute the joint values, okay. So the process that is automatically happening in human brain has to be done by programming in robots, okay. So that is actually the challenge, okay. For moving from A to B, for us it's very simple. We can use our legs and walk. But what is the case of robot? Imagine if it is a wheeled robot, 2 wheels, okay, left and right, 2 wheels. How can a robot can move from A to B? There are many challenges, like if a robot is placing in one position and if it is moving to another position, there can be obstacle, right? There can be obstacle. So one challenge is avoiding the obstacle, right? And robot doesn't know the shortest path. Like if you go from one point to another, human will choose the shortest path, right? What about robot? It should choose a shortest path, right? So we have to write a software, or we have to create some algorithms or techniques to find the shortest path, okay. Then we have to apply in robotics, okay. So I think you got an understanding, right? Like if humans are doing a lot of tasks, human doesn't understand the complexity because our brain is very, very intelligent and brain is solving a lot of things. But in case of robot, we have to implement everything in programs, okay. Then only this machine will move, or like move from one point to another, okay. So that's where these terminologies coming, like kinematics and dynamics, okay. Two of the terminologies are kinematics and dynamics. So the kinematics mainly talking about the motion of the robot, and dynamics is talking about the force and acceleration thing, okay. So when you move our hand, we are not conscious about how much force we require to pick this object. It will automatically calculate, right? But what about the robot? It should calculate the torque, right? It should calculate how much load each motors has to apply to pick this object, right? For our, it will automatically come from our muscle, okay. So the robot kinematics is one terminology that we are talking about, and the kinematics is about like there are two terminologies, sub-terminology, that is forward kinematics and inverse kinematics, okay. So the forward kinematics is like so for a robotic arm, the hand is called the end effector or the gripper, okay. So the gripper position is very important because gripper is the main area where we are interacting with the world. For example, I'm taking a mobile using the gripper, then I'm taking my water bottle with the gripper. So in robot also, we are interested in the gripper position, okay. For example, I just want to move the robot gripper position from A to B, okay, A to B, and take some object, then come to another position, okay. So we are mainly interested in computing the gripper position, and rest of the joints are joints, just the joints, okay. So we have a gripper and we have a lot of joints, motorized joints. And so the forward kinematics is simply it's a calculation, like if we give set of joint values to these joints, okay, then the forward kinematics equations, okay, these are a set of equations, can compute the end effector position, okay. For in case of robot, like if there is a 6 joint or 7 joint, if we are providing with 7 joint values, then if we put these joint values into some equation, then that equation will say what is the position of the gripper, okay, the end effector position, XYZ roll PTO. That is the 3D position, right? XYZ, roll, pitch, yaw. That is the, XYZ is the position, roll, pitch, yaw is the orientation. Okay, so that is the forward kinematics. Okay, so imagine we are giving some joint values to the robotic arm joints. Then using the forward kinematics equation, we can compute the gripper position. Okay, so in case of mobile robot, okay, the forward kinematics, we talked about the robotic arm first. Then in case of mobile robot, okay, if we give the wheel velocity to this equation, forward kinematics equation for mobile robot, if we provide with the wheel velocities, the speed of the wheel, okay, imagine there are two wheels, left and right, and if we give the wheel velocities to this equation, it can compute the position of the robot, position and orientation of the robot. Okay, imagine if the robot is moving with 0.2 meter per second or something, okay, then it can compute the current position of the robot with respect to an origin. Okay, so that is the forward kinematics. Just giving the velocities, just giving the joint angles, then it will compute the end effector. Okay, now the next terminology is inverse kinematics. Okay, so that is just opposite to this concept. Okay, and that is one of the important point or one of the important topic in robotics. The thing is, I have an object here. Okay, this is a remote. For me to take this object is very easy. I can just like move my hand and take this object. Okay, but for robot only know the position of this remote. Okay, the position of this remote. And so the inverse kinematics talks about if we give an XYZ roll, pitch, yaw value of the end effector, okay, then this equation, the inverse kinematics equation, will solve the values for joint values. Okay, like if we give the position of the end effector here, okay, if you are giving an XYZ roll, pitch, yaw, the position is here. Okay, the final position, goal position for the robotic arm gripper or the end effector is here. Okay, then the initial position of the robot is here. Then using the inverse kinematics equation, if we give a goal position, then the equations will solve the joint values to reach to this position. Okay, if you have any confusion, you can ask. Okay, so it's like the reverse of forward kinematics, and this is one of the most useful equations in robotics. Okay, like if you give a goal position or end effector position, the joint values will be computing. Okay, and it's a very complex max actually. Okay, like if you increase the number of joints, then the complexity of the calculation will be increasing. And and the computation required for solving the joint values is again high. Okay, and there are many methods, like in order to reach this position, for example, this is the goal position and my hand has to go, robot arm has to go to this position. Okay, so I can move my hand in different way, like I can go like this, I can go like this, I can go like this. Okay, so from the inverse kinematics equation we will get many solution. Okay, many solution for the joint values. So we have to optimize it somehow to find the best way, best path. Okay, so best joint values. So again, inverse kinematics is a very big subject. Okay, and you can find a good explanation, and you can find a very good explanation from the handbook of robotics. Okay, so that is the case of robotic arm. And what about a mobile robot? Okay, mobile robot involved not only wheel robot, leg robots and everything. So in case of mobile robot, the reverse thing that we have discussed, like if I'm giving a goal position, okay, if I'm giving like hey robot, just go to x1 y1 position, for example, then if I'm giving a goal position, the robot will go from the current position to the goal position. Okay, so if I give a goal position, the robot has to find the required wheel velocity to reach the goal position. Okay, for example, robot goal position is here and robot position is here. Okay, so in order to reach to this position, okay, the robot has to generate the velocity. Okay, compute the wheel velocity. If it is a two-wheel robot, the inverse kinematics equation should find the wheel velocity to reach to this goal position. Okay, again a very useful concept. Okay, I just mentioned a link here. So yeah, hi Justin.
For the inverse kinematics, you said the wheel velocity, sir.
Yeah.
But it will be the maximum velocity, sir. I don't understand why it has to calculate a specific velocity. Like
Can,
if a motor has a specific velocity, it will, if it has to reach a position, it will go at its max velocity.
No, like the velocity of the motors can be changed. Like for example, there is in the motor specification there is an RPM, right?
Yes,
yeah,
sir.
so that is the maximum speed rotation that that the motor is doing per minute. Okay.
So like only for the rotation we need to calculate. So like when it is a straight line, like it is going diagonally, first it has to turn and then go straight.
Yeah.
For a straight part, it has to be the max velocity of the motor.
No, not like that. Actually, like in order to reach it may not be the maximum velocity always. Like for example, if you are moving, I mean, if you are driving a car, for example, will we start the car with maximum acceleration? I mean, maximum speed? No, right? Like we will start and gradually start the speed, right? So like that in robot also there is a thing like that. Okay, so when we give a goal position, the robot velocity should be increasing gradually. Then after increasing some time, it will go to the maximum speed. Then when it reaches the, I mean, before reaching the goal position, it will be slowing down. It will decelerate. Okay, so that's that's how the velocities are calculating. It's not like when you start.
And one more thing, we need to give also the obstacles. Like, because the robot will always find the shortest path, and if you're not specifying the obstacles,
so
inverse kinematics what it follows.
Yes, so inverse kinematics is only caring about the I mean, going from A to B without any obstacles. Okay, it's only like calculating. Okay. But in order to incorporate the obstacles, we have to like put some sensors, and we have to I mean, additionally run some obstacle avoidance algorithms as well. That is the case for robotic arm as well. For example, I just want to move my arm from, this is a goal position and this is my arm. So I just want to move the robot arm from here to here. Okay, that is my objective. Okay, so there is an obstacle here. Okay, so the planned path should be like here to here. That is the I mean, the best path. But the shortest path will be this, and there is a chance for collision, right? So in case of robotic arm and in case of mobile robot, the obstacle avoidance is a separate topic actually. Okay, so when you try to find the inverse kinematic solution to this goal position, we will get many posts. Okay, many solution actually, and then that solution is feeding into an obstacle avoidance or obstacle detection algorithm. Okay, so that algorithm will filter the obstacled solutions. Okay, the solution which is having the obstacle. Okay, then it will only give the I mean, the correct path without obstacle. Okay, so that is what's happening, and I think we are discussing that in our course. Actually, there is Move It and Navigation Stack, so that is actually handling obstacle and path planning and everything. Okay, yes. Is that clear?
So for inverse,
Yeah.
so for inverse kinematics, the shortest path is not always compulsory.
Um, it's actually, yeah. So the goal is like moving from A to B, and it will actually find the best or shortest path.
Okay.
Okay, so it's trying to find the best path that is, I mean, from the current paths to the, I mean, goal position. Okay, so if we have an obstacle and all, then we have to, I mean, reroute basically. I mean, that's again like we have to feed the inverse kinematic solution to the obstacle avoidance algorithm. Then that obstacle avoidance algorithm will plan, I mean, select the best path which is not having obstacle. Then the robot will follow the selected path.
Okay, sir.
Okay,
Understood.
yes. Yes. Okay. So this is an example for inverse kinematics. You can see the robot is moving through some points. Okay. The end effector of the robot is moving through some specific points, and you can see the join values are automatically adjusting. Okay, so we are only giving the end effector position. Okay, you can see these dots, right? So these dots are the inputs to the inverse kinematics algorithm. Then that inverse kinematics algorithm will compute the join values. Okay, so yes, so this is one of the challenges in robotics, the kinematics and dynamics. Okay, yeah, so that is the manipulator kinematics, and you can find the mobile robot kinematics. Okay, so here this algorithm is I mean, you can find a path is planned. Okay, and it is also taken care of the obstacle. Okay, so you can find it's avoiding the obstacle and planning a path and going to the goal position. Okay, yes. Yeah, now I just want to mention about the dynamics. Okay, so currently the kinematics only mentioning about the motion. Okay, but in our case, in human, it's not only about motion, right? There is a force involved. For example, if I'm taking my water bottle, okay, then I have to exert some force on this on this water bottle. Okay, so then it's not only about motion; it's about force and acceleration as well. Okay, so the robot dynamics is again a complex problem. So if you can see the Boston Dynamics robot and all, so they have modeled the kinematics and dynamics very accurately. Okay, so the dynamics is like it's a study of force and acceleration. Okay, acting on the robot. Okay, so again forward kinematics and inverse kinematics. So it's also called the rigid body dynamics. Rigid body means like a robot is treating as a rigid body, like it will not change the shape when we apply the force. That is actually called the rigid body. So the robot dynamics or rigid body dynamics, again two things like forward dynamics and inverse dynamics. So forward dynamics is like given the forces and work out the acceleration. Okay, we are directly giving the forces in each joint, and then it will compute the acceleration. But the inverse dynamics is we are giving the acceleration of a joint, I mean end effector or something, then it will work out the force required to move move the joints. Okay, force required in each joints actually. Okay, so this is two terminologies, kinematics and dynamics. I think if you are going for masters or something, you can you can find these topics, and maybe I can also show you, just a sec, in yeah. Oh, I also forgot to share this course with you. Just a second. So this is one course that I can suggest to you. Like if you are planning to uh, explore more on robotics concepts, I think this playlist, okay, I think it's a playlist, modern robotics, I think you have seen a book of modern robotics. This course is actually from Northwestern University, and they are discussing about almost all the robotics concepts. Okay, you can find it here. um, yeah, and they are using VREP Copilia Sim for the simulation. They are not using ROS, I guess. You can find they're working with the forward dynamics. You can find, I'm just playing the videos. Okay, and then they're actually explaining it using some simulators. This is called Copilia Sim, which is available for free. Then yeah, I think it's actually very vast. They are covering most of the things from the book. Okay, yeah, I think this will be a good reference for you to understand. They are also covering mobile robotics. You can find the odometry and all here. Then mobile manipulation. I think it's completely based on the book. Okay, there is a book actually from Northwestern University. Okay, yes, and for working with mobile robot, I think they're using yeah, simulation. So on the top you can find the differential drive, then omnidirectional. Okay, yeah, I just want to like share this content with you. Okay, I think it will be useful to you. Okay, to understand the concepts in detail. Okay, so you can just explore various concepts. I think that video will be good for a reference. Okay, okay, so I'm not going in deep. Instead, I'm giving this reference. Okay, I think you can explore the robotics concept using these lectures and also the handbook of robotics. Okay, so now some interesting stuff. So this is one of the important section in this in the entire section. So this is about how to build your robot. I mean, the steps, various steps that we have to follow to build a robot. Okay, so if you are trying to build a robot, I think I have seen most of the students, even I have tried the way, like I will directly jumping into the hardware. Okay, directly jumping, I'm directly buying the hardware and trying to program it. So the problem is, if you are working with a low cost robots, then that is fine. But if you are trying to work with very expensive robot or very complex robot, then the thing is that like if you are directly buying the hardware, and if that is not suiting for your purpose, okay, then you have to buy another one. Okay, so there is a problem with choosing the sensors, computers, then actuators. Okay, so that is very important in building robots. Sorry. So how to select better sensor, better computer, and better actuators for your robot application, that is actually deciding by these steps. Okay, rather than assuming things, you can follow this step and you can end up in selecting the best components for your robot. Okay, so first is like if you are planning to design a robot, I mean if you are planning to create a robot, first you will get some requirements, right? For example, if you are working with some robotics competition, or some, if you are working for some product development, then the client will actually send you with some requirements. Okay, So that is the first phase, the requirement gathering. Okay, so you have to collect all the requirements from the, maybe from competition or from the client. Okay, so if you are collecting more and more requirement from the client, then uh, they should be in the same page. Otherwise what happening is that the client will say like, you have to build a mobile robot and it has to deliver the food. Okay, that is an abstract requirement. Okay, but if you are not collecting more requirement, then what happening is that when you start working with or start designing or creating the actual robot, then the client will say, hey, this is not the plan I had. Okay, I had a different plan. Okay, so that's what the importance of requirement gathering. You have to collect maximum requirements from the clients. Then the first step, that is a robot designing. Okay, so the robot designing is like, you have to model the robot using max. Okay, so this is what happening in the robot designing. You are going to design a machine, right? You are going to design a intelligent machine. So you have to compute various stuff, like if the robot is wheeled robot, then you have to compute the torque required to move this robot, then the speed, then the voltage, then there are a lot of parameters associated with a robot, right? So you have to compute all this stuff, okay, in the design phase. Okay, and even you should have some some sketches as well of the actual robot. Okay, so after designing, you can do the 3D modeling of the robot. Okay, maybe very detailed. If you are working for a product, I think it will be better if it is detailed, but if you are working with some prototype, I think simple model will be also fine. Okay, so you can start modeling using ROS URDF. You can use it, or you can use some 3D modeling software like SolidWorks, then Fusion 360, then Blender you can use, okay, for modeling. So it's like conceptualizing the actual robot. Okay, so if you model the robot in 3D, you can see how the robot looks like. Not only to visualize the robot, but you can assign the dynamics parameters of the robot, or the kinematics and dynamics of the robot. The kinematics, talking about the motion, so it will have the links and joints of the robot. Then the dynamics involve the mass, inertia, force, all this stuff. Okay, so in the 3D modeling software, you can model all those stuff. Okay, so that is the advantage of 3D modeling. And also one more point is that you can use these 3D modelings 3D model to do the simulation. Okay, which is one of the important step if you are building a complex robot or expensive robot. Okay, so the simulation is actually the we are giving a life to the 3D model. Okay, and we are putting in a virtual environment. Okay, then you can start working on the robot, the virtual robot. Okay, so it will have all the parameters of the actual robot. Okay, but we already built it without spending any money. Okay, currently we have the virtual robot ready. Okay, and you can play with it without spending any money or any cost. Okay, so that is the flexibility in simulation. Okay, and the good thing is that if you have the simulation, then you can understand the issues in your design, you can correct it. Okay, and also you can start programming your robot using the simulator. Okay, and also, yeah, so there are a lot of benefits if you are doing the simulation first. Okay, then after verifying your design using simulation, you can go to the prototyping or the fabrication using the 3D printing, or using CNC machines and all. You can start the fabrication. Okay, then finally you can write the robot software. Like, you can start developing your robot software from the simulation, and after prototyping you can move your software from the simulation to the actual hardware. Okay, then deploy and testing. Okay, that is not mentioned here. Okay, So these are the important or like abstract steps that you have to follow in order to build a robot. Okay, so I think if you are following this, then you can end up in a better design. Okay, yes, so these are the process. Okay, now I'm just concluding with this slide. Okay, this is the last slide. I mean the last slide for this session. So this slide is talking about oh, maybe we can cover a few more slides. I think there are only 4 slides left. Okay, so after doing all these things, I think we can build our robot, right? So while designing, okay, you have to select the sensors, you have to select the actuators, you have to select the brain of the robot. Okay, so I just documented these 3 things, okay, in this blog. Okay, let me share this. I will also make this also put this on the notes. No worries. So you can find how to choose sensors. Okay, basically I'm talking about different kinds of sensors and its application. So from this you will get an understanding which sensor you have to choose for a particular application. Okay, and also which actuator you have to use for particular application. Okay, so I have documented many actuators. So you can select it according to your requirements. Okay, and also the brain of the computer, brain of the robot. So from the microcontrollers to different computing unit like Raspberry Pi and all. Okay, so I have documented all these things. So your assignment is like just go through these uh, materials. Okay, next week before the next session. Okay, so you will have a better understanding about different components of robot and how to select it. Okay, so that is this slide. And finally we can talk about how to program. Okay, like our entire course is about the programming of robots. Okay, using ROS. So coming to the programming, if you can see, like there are different programming languages that we can use in robots, mainly C++ and Python. That is the most popular programming languages that we are using. Just a second. Then we can use Java. I mean, any language, but the most popular languages are C++ and Python. And the important software frameworks that we are using is ROS, then OpenCV, then Gazebo, that is for simulation, then ROS 2, then ROS 1 and ROS 2, OpenCV, Gazebo, and Point Cloud, which is one of the other library. OpenCV stands for Open Source Computer Vision, mainly for robotic vision related tasks. Then ROS is for message passing. We will discuss that. Then Gazebo is for simulation. Then PCL, Point Cloud, you can just Point Cloud library, is for 3D processing, 3D point cloud processing. Okay, so so these software frameworks are useful while programming your robots. Okay, commonly, and we will discuss all I mean, in our course we will discuss all this stuff like ROS 1, ROS 2, OpenCV, Gazebo, PCL, and yeah, all this stuff. Okay, so this is what we are using mainly for the programming part. Okay, and also, like if you are prototyping small robots, you can simply use Arduino for maybe you can prototype the robot using a single microcontroller. So for that you can use Arduino or a Raspberry Pi or something like that. Okay, yes, so now it's a time for discussion. We can do a Q&A. After that we can conclude. So if you have any question, let me know. We can discuss. Okay, time for Q&A. Let me know if you have any questions. Any questions, guys? Is it clear?
Sir, in programming languages, you said SCADA, sir. Which SCADA, sir? It is like the one which the PLC one or something else,
Yeah,
sir?
yeah. Actually, I mentioned I actually mentioned the industrial program, the PLC programming.
Okay.
Yeah, and the rapid programming. I'm not sure you heard about. Rapid programming is using for industrial robotic arms, uh, especially for KUKA robot. They have their own programming language. So that's what I meant. Yeah. Yes.
Sir, what is this OpenRAV used for?
OpenRave. Yeah. So it's again a framework, but it's not actively maintaining. But it's for motion planning mainly, simulation, motion planning, and all. You can see here. It's a motion planning library. So you can use it for doing inverse kinematics. Then motion planning. Motion planning means like um, if the robot wants to move in a specific trajectory, you can do the motion planning using this library. You can just visit their website, but I think it's not actively maintaining. This is the website of OpenDrive. Yes, I mean there are multiple uh, libraries and frameworks available in robotics, but I just mentioned the popular one. Yes.
Okay, sir.
Let me take the book. Just a sec. So, so next week, yeah, this weekend or next week, if you get time, just go through. No need to read everything, but just scroll these concepts like kinematics, dynamics. Okay, so it will be great if you can just go through it, okay, and understand the concept. Also, the video that I have shared, the modern robotics. Okay, it will be better. This book mentioning everything. You can find dynamics, then kinematics. Okay, so there are many other concepts. Okay, so you can just go through it. Maybe going through the abstract will be fine, so you will get an understanding. Okay. Okay then, guys. Can we conclude then? Can we conclude today's session?
Not.
Okay. Okay then, guys. I think we can conclude today's session, and the next session will be on next Friday. Okay. Maybe like I'm planning to take some vacation from December 1st. So I will announce the time. Okay. I will be traveling from December 1st, I think. So I will be announcing the new time. So yeah, so that is one update from me. So this week, let me check the timing. So we can do the session on 26 and 27. After that, from December 1st, I will announce a revised timing. Okay. Yes. Okay then, guys. If you have any questions, further question, you can post it in Discord. Okay. And if you have any questions related to ROS or robotics, I think you can ping Jerin or Rajesh as well. If I'm not available, they can also come up with better solutions. Okay. Okay then, guys. Have a nice day and see you next week. Okay. Okay then. Bye.